Welcome to this lecture on advanced electric drives. In the last lecture, we were discussing about the control of synchronous motor drive, and we have seen that the synchronous motors are actually applied for very high power application, especially the wound field synchronous motor, where the field winding is mounted on the rotor, and this kind of synchronous motors are applied for very high power application beyond 1 megawatt rating. And we have also seen that when we control the synchronous motor, there could be two modes of operation. One mode is called a true synchronous mode, in which the synchronous motor is applied from a voltage source of independent frequency. Say for example, it could be a synchronous motor connected to an infinite bus. So when a synchronous motor is connected to an infinite bus, the infinite bus frequency is fixed, and that is independent of the rotor speed. And hence, sometimes the synchronous motor undergoes hunting and instability. When the rotor speed is different from the synchronous speed, the synchronous motor exhibits hunting. And sometimes if the load is very high and if it is suddenly applied, it may also lose synchronism, which is instability. So when we talk about a synchronous motor under true synchronous mode, as we have seen in case of an infinite bus feeding a synchronous motor, the applications are limited, not mainly for the variable speed application. But when we talk about variable speed application, we want the speed should be continuously variable from rest to the full speed, and hence a closed loop becomes necessary, and that is called a self-controlled synchronous motor, where the rotor position is used to determine the voltage applied to the stator. Hence, the rotor frequency or the rotor speed is tied with the stator frequency, and hence there is no question of falling out of step, there is no question of hunting, and hence the motor becomes a stable one at any given speed. And one of these examples that we are discussing in the last lecture was that of a CSI fed synchronous motor. The motor is being fed from a CSI, a force commutated CSI, and the application could be for fan application, could be for pump application, but especially for high power application. Let us see the circuit diagram of a CSI fed self-controlled synchronous motor drive. Now this is what we are discussing in the last lecture, that we have a converter, and this converter is a AC to DC converter, which could be a control rectifier, which is changing the three-phase AC supply to a DC supply, that is VR. VR is the output of the converter, which is a DC supply. Then this is fed to the DC link, and this is the DC link, and the DC link has a very high inductor. This is the inductor in this case, and the purpose of this inductor is to keep the current approximately constant. And then we have the CSI, and the CSI is a force commutated CSI, and the outputs are the three currents IA, IB, IC, which are feeding the synchronous machine. The field may be separately excited. We may as well have a field winding here. This could be the field in this case, and field in this case can be excited separately. It is a wound field synchronous machine, so we can excite the field separately by DC source. We have slip rings and brushes, and this is the field. The synchronous machine, when it is self-controlled, requires a position sensor. The position sensor, the rotor position sensor, is essential to determine the phase angle of the applied voltage, so that the rotor and the stator are always synchronized. So we can have an encoder here, and this encoder will be used for determining or finding out theta r. Theta r is the angle of the field or the rotor with respect to the stationary phase A axis, and this rotor angle can be used to determine the phase of the applied currents, that is IA, IB and IC. So we define an angle gamma. Little later we will see what is the significance of this gamma, and we have a phase shift of pi by 2, and we determine, and this angle that we get here is gamma plus theta r plus pi by 2, that is fed to the CSI to determine the phase of the current that is injected into the phase A, phase B, phase C of the stator of the synchronous motor. And to vary the speed, we need to control the current, and hence we control the voltage, that is VR of the converter. Voltage VR is controlled by controlling the triggering angle or the firing angle of the 3-phase converter bridge. This is basically consisting of SCRs. So we can control the triggering angle of the SCR to be able to control the DC link current, and which in turn will control the torque and the speed of the machine. Now this is the complete power circuit. To be able to understand the operation in detail, we will be only talking about the steady state operation. We will ignore the transient for the time being. We will only concentrate on the steady state operation of the drive and try to draw an equivalent circuit of this CSI fed synchronous motor drive system. Now let us see that in this DC link we can apply the Kirchhoff's voltage law, that is VR is equal to R DC into II plus VI. VI is the inverter input voltage, and if we multiply both the sides by II, we can say that VR into II is equal to R DC into II square, that represent the loss in the DC link. The inductor that we are using can have a resistance that is RDC. RDC is the resistance of the inductor, the DC link inductor, and RDC into II square represent the loss in the inductor, and plus VI into II, that is the input to the CSI. So what we see here is that the power is entering the CSI and then it is going out of the CSI. So in this case we can assume that the inverter is having 100% efficiency. There is no loss in the inverter in the ideal case. So if we assume that the inverter does not have any loss, whatever is the input to the inverter will be the output of the inverter. The input is the DC power and the output is the AC power. So this VI into II represents the input power to the CSI. Now we can see here that this VI II is the input power. That is equal to this equation. We can manipulate a little bit. We can take out this VI II, and then if we simplify, we will have VR into II minus RDC II square. Now this VI into II is the input of the CSI, and we have assumed that the inverter is lossless, and hence the input should be equal to the output, and that is equal to the input of the motor. The motor power factor is cos theta, and the per phase voltage is VA, and per phase current is IA. So we can say that the output of the CSI is 3 into VA into IA into cos theta. Now this is the equation, this is the power balance equation. Whatever is the input, the same is coming as the output, and the output of the converter minus the losses in the DC link is the input of the CSI or the current source inverter, and the current source inverter is lossless, does not have any loss. So the input is same as the output, and what we have here is that the output of the CSI is the input of the motor, which is 3 into VA IA cos theta. Now let us draw the phasor diagram. So if we draw the phasor diagram here, we can start with, let us say, the field axis. So this is our field axis. So we can say this is as the D axis. So we can show the field pole like this. This shows the field of the synchronous machine, and then the Q axis is right angle to the D axis. So this is our Q axis, and this angle is 90 degree, and of course the field current is in the direction of the field axis. So, we can say this is IF, this vector is IF, IF is in the d axis, and the field induced EMF, this IF is induced some open circuit voltage, that voltage is in the q axis. So, this is our EF. We know that the induced EMF and the flux or the MMF are right angle to each other. So, the EF is along the q axis and IF, which is inducing EF, is along the d axis. There is a quadrature relationship between the flux and the induced EMF, which is very well known from the DC machine. We know that the field is in the d axis and the induced EMF in the armature is in the q axis. Similarly, in case of synchronous machine, if we take the rotor reference frame, the field MMF is in the d axis and the field induced EMF is in the q axis. Then we have the current, and the current can be in any arbitrary direction based on the power factor. So, let us say that this is the current, armature current IA. So, if this is the armature current, we know that in case of a motor, we can write down this equation, that the applied voltage V is equal to EF plus J IAXS plus IARA. This is a phasor equation, this is a steady state phasor equation. We have ignored saliency for simplicity, and synchronous reactance is XS, the armature resistance is RA, and IA is the current phasor, it is a phasor quantity in the steady state condition. So, this is the equation of a motor. So, we can translate this equation into a phasor diagram. So, in this case what we have here is that we have EF and we have IA, and we can of course draw JIAXS. So, what is JIAXS? So, we can draw this, this is the current, and the current and JIAXS will be right angle to each other, and then we have IARA, and IARA will be in this direction. So, these are all phasor quantities. So, we have to show them appropriately by phase angle and amplitude. This is IARA, and the resultant of this would be the terminal voltage, that is V or VA. We can call this to be VA, and this is the power factor angle. So, we can say that the angle between VA and IA is theta, theta is the power factor angle, and this angle, the angle between phase A current or the current phasor and the q axis is gamma, and this actually is a rotating phasor, each one is a rotating phasor, and these are DC variable. When we talk about the rotor reference frame, rotor is rotating at a speed of omega r, this is moving at a speed of omega r. What about the stationary phase? Now, if we see the stationary phase, we can have a reference for the stationary phase, that is the phase A. The phase A axis is the reference of the stationary phase. So, we can say this is the phase A axis. So, if you take the phase A reference, in this case, this angle that the rotor subtends with phase A is the rotor angle, that is theta r. Rotor is moving away at a speed of omega r. So, theta r is angle between the d axis of the rotor and the reference phase A axis, which is stationary. Now, if we see the phase angle of the current, that is IA, what is the phase angle of the current? This phase angle of the current is with respect to stationary phase A axis. That is equal to, we can say this is equal to theta r plus pi by 2, this angle is right angle. So, we can add a pi by 2 here, plus gamma. Gamma is the angle between the q axis and phase A. So, this basically, this phasor diagram is also a space phasor diagram, because these are also, there is a one-to-one correspondence between time phase and space phase. So, if we take a snapshot in the machine and if we visualize all this induced EMF, the MMFs, the flux linkages and the voltage drops in the space, this would be the representation in the space. So, we can call this to be a space phasor diagram as well. So, if we want to find out the phase angle of the current phasor with respect to stationary phase A axis, that will be theta r plus pi by 2 plus gamma. That is what we are talking about little earlier, that if you want to find out the phase angle of phase A, let us say, that is gamma plus theta r plus pi by 2. Of course, the actual currents are IA, IB, IC, and once we find out the phase angle with respect to IA, we can find out the phase angle with respect to IB and IC also, because the phase B and phase C are shifted from phase A by 120 and 240 respectively. So, this is what we have here, that we have the phase angle of the current phasor with respect to the stationary phase axis is theta r plus pi by 2 plus gamma. So, this is the phasor diagram that we have, and from the phasor diagram we have to find out what is VA cos theta. Now, we can write down the expression for VA cos theta. Now, if we find out the expression for VA cos theta, what we need to do is the following. This is axis of VA, I mean IA. So, if we project this VA along IA, we get VA cos theta. Now, what are the other voltage drops on the same axis? So, what we do, we project the other voltage drops also on the same axis. The other voltage drops are EA, EF into cos gamma plus the resistance drop, that is IARA. So, what we do here, we replace this VA cos theta by EF, the field induced EMF, into cos gamma plus IARA. So, if we substitute that and simplify, what we get is the following. So, we have the original equation here, that VI II, that is equal to VR II minus RDC II square, that is equal to 3 VA IA cos theta. So, we can replace that in the following fashion: VR II minus RDC II square, that is equal to 3 IA into VA cos theta is EF cos gamma plus RA IA. Now, here in this equation we have two currents. One is II, this is II, and then we also have IA. IA is the motor currents, this is the motor fundamental component of current, and II is the DC link current, and there is a relationship between the DC link current and the motor fundamental component of current, and the relationship can be derived as follows. We know that in a CSI, if we see the output current profile of a CSI, it is basically like a quasi square wave current pattern. This is our time axis, or omega t axis like this, and then this is IA. Say for example, we are talking about the phase A currents, and the peak value of the current is II, is the current of the DC link. The DC link current is reflected in the AC side, and the current in the AC side is not a sinusoid, is basically a quasi square wave when the inverter is a current source inverter. Now, this quasi square wave current will have a fundamental components and will have so many harmonics. So, we ignore the harmonics because harmonics do not contribute to the torque production, I mean the fundamental torque production. When we are talking about the average torque production, we are only concentrating on the fundamental component of current, and that has to be derived. So, this can be broken down into a fundamental component of current, which is sinusoid, and this is having this width of 120 degree. Similarly, in the negative half cycle also this is symmetrical 120 degree, and this duration between the two pulses here is 60 degree. So, we can find out what is IA. IA is a fundamental component, RMS value of the fundamental component of motor current, that is equal to 1 by root 2. The peak value of this fundamental component is 4 II by pi into cos of 30 degree. This can be easily derived by finding out the Fourier series of the current. So, we keep the fundamental component and the expression is given as follows. So, we can simplify that. So, we have 2 into root 2 by pi II, cos 30 is root 3 by 2. So, what we have here is this, that this is root 6 by pi into II. So, what we do here is that we replace this II by IA. So, we can say that this implies II is equal to pi into IA by root 6. So, we can substitute this in this equation. So, in this equation what we have, we can take the values of II and replace this II's by pi by root 6 into IA and find out the final equation. So, we can find out the final equation. So, we have VR into pi by root 6 into II. We have replaced II by pi by root 6 into IA here, minus RDC II square. So, II is pi by root 6 into IA. So, we have here pi square by 6 into IA square, that is equal to 3 IA. Here we do not have to replace, it is already in IA, EF into cos gamma plus IA into the resistance, and the resistance here is RA. So, this is what we have here, and we can divide the left hand side and the right hand side by 3 and club these current parts, and there will be cancellation. We have IA here in the left hand side and the right hand side. So, IA will be cancelled. So, what we have finally is the following: pi by 3 into root 6 into VR, that is equal to EF into cos gamma plus IA into RA plus pi square by 16 into RDC. So, this equation is a steady state equation. We have ignored all the transient conditions, and we see, of course, this is basically something like a DC equation. There is no inductance term here, there is no LdI by dt term here. So, this is something like a DC equation. So, we can write a steady state equivalent circuit based on this equation, and the steady state equivalent circuit is shown as follows. So, what we have here is the applied voltage pi by 3 into root 6 VR, and then we have the resistance here RA, then we have the decelerating resistance pi square by 18, this is pi square by 18 into RDC, and then we have the back EMF, which appears as EF cos gamma. So, we can call this to be a steady state DC equivalent circuit. Now, this DC equivalent circuit will be sufficient to find out the steady state torque and steady state speed. So, if we are only interested in the steady state response, means steady state speed and steady state torque, we did not consider the transient conditions, and this equivalent circuit is going to give us the steady state response of the CSI fed synchronous motor drive. Now, this resembles that of a DC machine. We have seen that in case of a DC machine, we have a resistance and we have a back EMF in the armature, and the field is separately excited. We can keep in a special situation the field current constant. So, in a synchronous machine like this, we can keep the field current constant, and if we want to change the speed, we change the converter voltage, and the converter voltage is VR. So, if we change this VR, we will have an increased current, and the current in this circuit here is IA. So, if we increase VA, IA will be increased, and if IA is increased, there will be more and more torque, and the speed will be increased. Now, let us find out the expression for the mechanical output power and the speed. So, here in this case what we have, the power here P make is power coming out of this, the gross mechanical power, and this mechanical power is the product of current into the induced EMF. So, the current is IA, is a DC circuit, there is no phase angle, and this induced EMF is EF into cos gamma. Now, this is a per phase equivalent circuit, because we divided this equation by 3. So, we can say it is a per phase circuit. So, the synchronous machine has 3 phases. So, if we want to find out the total mechanical output power, we have to multiply this with 3. So, we can multiply this with 3 here, and then this is the total mechanical power, and if we are interested to find out the torque, the mechanical power has to be divided by the mechanical speed. So, this is what we have, and then if you want to find out the torque, in this case TE is P make by omega R m, and omega R m is the mechanical speed. We can replace that by the electrical speed divided by pole pair. So, we can multiply that by pole pair, this equation by P by 2, and P by 2 is pole pair, because P is the number of poles, and we can substitute the value of P mechanical. The P mechanical is 3 IA EF cos gamma. So, 3 IA EF cos gamma by omega R E, and we multiply that by P by 2, then we can say that this is 3 P by 2 into IA, and the induced EMF we can replace by lambda AF is the field flux linkage into omega R E into cos gamma divided by omega R E. Here we have assumed that the field induced EMF EF we have assumed to be the field induced EMF, and that is the induced EMF in the armature due to the field current, and we define a flux linkage called lambda AF, which is the flux linkage in the armature due to the field current. So, this EF is equal to lambda AF into omega R E. If we assume that EF equal to lambda AF into omega R E, we can write that here, and then finally the expression for the torque is 3 P by 2 IA lambda AF into cos gamma. Now, this equation is a very simple equation which resembles that of a separately excited DC machine. Of course, gamma in this case can be kept constant. Now, if we keep gamma constant and field flux constant, it means this is constant and this is also constant. We are not interested to change the field current, we keep the field current constant. The torque can be controlled by controlling the armature current, and that is something like a DC machine. And if we want to maximize this torque, we make gamma equal to 0. We know that we have a freedom here because we have a CSI, and in the CSI we can have any phase angle, and gamma in a special case can be equal to 0. So, if we keep gamma equal to 0, the torque is maximized, and that is something like a torque of a DC machine, because the current is only in the q axis and the field is in the d axis, because gamma is equal to 0 and the torque is maximized. So, we can say here that if gamma equal to 0, we can say that TE is equal to 3 p by 2, these are constants, into IA into lambda AF. So, that is similar to that of a separately excited DC machine. So, it means whenever we have a closed loop position feedback, we can control the synchronous machine like a separately excited DC machine. So, and in this case the torque is also maximized. So, this equation shows that the torque in this case is controlled like that of a DC machine. We can keep the flux constant, that is lambda AF constant, and we can change IA to control the torque. Now, in the very beginning we assume that the CSI is force commutated. Now, in many situations the CSI need not be force commutated. Say for example, the force commutation requires separate force commutating components like inductance and capacitance. So, if the CSI is to be load commutated, it means the CSI would be commutated by the back EMF of the synchronous machine. The power factor has to be leading. So, we will just briefly discuss that how the situation changes when we talk about a load commutated synchronous machine. So, we are talking about load commutated CSI fed synchronous motor drive. We will just talk very briefly about this. Now, for the load commutation, the power factor has to be leading. So, that is very important, that the motor power factor should be leading. So, if the motor power factor has to be leading, that has to be obtained by proper control of the synchronous machine. So, what we do here, we do not make gamma equal to 0, because our objective is to achieve leading power factor. We make gamma very large in fact. So, if gamma is very large, the power factor automatically becomes leading. So, for example, if you take the phasor diagram, we have the field current here, and we have the field induced EMF in this case, that is EF. This is the q axis, and this is the d axis, and here we deliberately make IA large. So, this is our gamma. Gamma is the angle between EF and IA. These are all phasor quantities. So, if this is our gamma, what about J IA excess? So, this is J IA excess. J IA excess, the synchronous reactance drop, and then we add this to the resistance drop, and the resistance drop is somewhere here, IA RA. So, we have the synchronous reactance drop, that is J IA excess, and we have the resistance drop, that is IA RA. Now, the resultant will be giving us the applied voltage. So, the applied voltage here is this vector, this is VA. Now, if this is VA, what about the power factor? the power factor is angle between V and I. So, we see here that the power factor in this case is leading. This angle is now theta. So, for load commutation, when the CSI has to be commutated by the back EMF of the machine, we have to make gamma large, and when we make gamma very large, the current leads the voltage and the power factor becomes leading. So, this is a discussion on the CSI effect synchronous motor drive, which is used for very high power application. So, let us now see how we can describe or how we can study the steady state response of the synchronous machine. Let us now see the behavior of the synchronous machine in the steady state condition. By steady state, we mean the speed is constant, the phase angle of the applied current is constant, the flux linkages are constant. So, we will try to derive the equations of the synchronous machine in rotor reference frame at steady state condition. So, we will try to write an equation for the DQ model, and we will consider the rotor reference frame. So, what is the meaning of steady state? By steady state, we mean the currents amplitude are constant. It means IA, IB, IC are constant, and the current phase angle is also constant. So, we can say that the current amplitude and phase angle are constant, which means IQS. In the rotor reference frame, we can define the currents in terms of D and Q axis currents, and the component of the current along the Q axis is called IQS. IQS is equal to capital IQS because this is a constant quantity. So, we can say this is constant. Similarly, the D axis current IDS is equal to capital IDS, that is constant. And then we can also consider the rotor flux linkages to be constant. Constant rotor flux linkages. So, this implies the damper winding currents to be equal to 0, because if the flux linkages in the rotor are constant, the damper windings do not have any current. So, IKD is equal to IKQ equal to 0. So, we can say here that damper winding currents are 0. This implies damper winding currents are 0. So, which means IKD is equal to IKQ is equal to 0. And we can also assume that the field current is also constant. The field is separately excited. So, we can assume that the field current is also constant. Constant field current, which means IF is equal to capital IF is equal to constant. Of course, the speed is constant. It means omega r is same as omega E is constant. The electrical speed of the rotor is same as the synchronous speed, the electrical synchronous speed, that is omega E. So, these are the conditions for the steady state. Now, if we consider the steady state condition, the equation for the stator voltages can be written as follows. So, we can write down the stator voltage equation, but before that we can derive the torque equation. So, the expression for the torque is given by, we know that the torque is equal to 3 by 2 into P by 2 into psi ds into IQS minus psi QS into IDS. So, here the flux linkages psi ds and psi QS can be expressed in terms of the inductances and the respective currents. So, we can replace the psi ds by LLS into IDS plus LMD into IDS plus IF, because the damper winding currents are 0. So, we need not write the expression for the damper winding currents here. This into IQS. Similarly, for psi QS we can write down as LLS IQ, this is the leakage component, and then we also have the magnetizing component LMQ into IQS IDS. So, this is the expression for the torque, and this can also be simplified. If we simplify that, the leakage components will be cancelled in this case. So, what we have finally is the following: 3 by 2 and P by 2. We have here LMD, IF, IQS, plus we have LMD minus LMQ into IDS, IQS. So, this is in terms of inductances. LMD and LMQ are the D axis magnetizing inductance and the Q axis magnetizing inductance respectively. And the first component here is the synchronous machine torque. So, we can say here this is the reaction torque or the synchronous machine torque or the field torque. This is better termed as the field torque. So, we can say this is as field torque. This is because of the field winding current. If the field winding current is equal to 0, this component of torque will vanish. And the second term is called the reluctance torque. This torque comes into picture when there is a difference of inductance between the D and Q axis. So, this can also be expressed in terms of the reactance. We are talking about a variable speed drive, and the reactance of the machine is defined for the base frequency, and the base frequency in radian per second we can call that to be omega b. So, we can also express that as 3 by 2 P by 2 1 by omega b into XMD IF into IQS plus XMD minus XMQ into IDS into IQS. So, this is the expression for the torque in terms of the reactance, and this is the steady state torque. So, in the steady state we have two components of the torque. One component is called the reaction torque or field torque, and the other component is called the reluctance torque. And the reluctance torque basically comes up due to difference of inductance between the Q axis and the D axis. If XDS or XMD is not same as XMQ, there will be a reluctance torque. This torque of course is not a very large amount, this is about 20 to 30% of the rated torque, but nevertheless this torque is present in the steady state condition when we talk about a salient pole synchronous motor. So, this is the expression for the torque. What about the voltage equation? The voltage expressions can be derived as follows. So, we are talking about the steady state voltage equations, which is very simple to write, and the idea of writing the steady state equation is that the the operating principle of the motor will be very clear, because in the transient condition we do not have much understanding of the machine, that only the thing is that we have some damper currents. So, the steady state equations are very good for understanding the working principle of the machine, the steady state torque production, the steady state flux, the speed, etc., can be obtained from the steady state voltage equations. Of course, in the transient condition, in addition to the field and the armature, we also have the damper currents, which will have some dynamics or which will delay the torque response. So, in the steady state condition, damper currents do not exist. So, what we have here is the following. So, we do not have any P terms here. The flux linkages are constant. So, we do not have any P terms, and all the quantities are the DC quantities, because we are talking about the rotor reference frame. So, we can write down the D axis voltage, that is equal to RS IDS minus we have the rotationally induced EMF, and the rotationally induced EMF is omega E by omega B into XQS IQS. So, these are the equation. This is the equation in the rotor reference frame. We do not have any P term because the flux linkages are constant, and we have omega E, and please remember that omega E is same as omega R, and that is also constant. We are talking about the constant speed operation, and at constant speed the electrical speed is same as the electrical frequency of the current. So, this is what we have here, and then what about the Q axis? VQS, that is equal to RS into IQS, and here also we do not have any P term because the flux linkages are constant. We have a positive rotationally induced EMF, omega E is same as omega R by B, and Q axis will have the rotationally induced EMF due to the D axis flux, and in the D axis, in addition to the armature winding or the stator winding, we also have a field winding. So, here what we have in this case is XDS IDS plus XMD into IF. So, this is basically the equation in terms of the reactances, because reactances are given at base frequency, and hence we divide that by omega B to obtain the inductance. So, this can also be written in the following fashion, that VDS is equal to RS IDS minus omega E. Instead of reactance, we can also have the inductance. The inductance will be LQS IQS. Similarly, we can have VQS equal to RS IQS plus omega B omega E into LDS IDS plus LMD into IF. Now, we have two equations, one in the D axis, other in the Q axis, and these equations are valid for any given speed. Omega R can be anything. It can be 2 radian per second, it can be 50 radian per second, it can also be 300 radian per second. It is valid for any speed, because we are talking about a variable speed drive. It is frequency independent. So, from this we can of course write down a phasor diagram. We can draw a phasor diagram based on the two equations, and the phasor diagram will be in two axis mode. We have voltage in the D axis and voltage in the Q axis, and accordingly we can show the voltage as vectors in the two independent axes D and Q respectively. So, we can draw the phasor diagram here. We have the Q axis in this case, and this is the d axis, and we have the field in the d axis, field pole, and the field current IF is in the d axis. We can show that to be IF here, this is right angle. And then what we will do here, we will first write down the q axis induced EMFs. We have this term LMD IF into omega E. LMD IF into omega E is same as the field induced EMF. So, we can say it is same as EF. So, we can write down that this is EF, the field induced EMF, as you have seen little earlier. And then what we have in this case, we have another induced EMF, that is LDS into IDS. That is basically a reactance drop. We know that we have two different reactances, and the MMF can be split into two axes, and the corresponding reactance will give the voltage drop. So, here this LDS into IDS will be this reactance. So, this is XDS into IDS, and then we add here the drop in the q axis, d axis. So, this is basically the d axis drop. If you see that this is our d axis equation, in the d axis the induced EMF is minus omega E into LQS into IQS. So, this component of the induced EMF will be in the negative q axis, negative d axis. So, this will be in the negative d axis. So, we can call this to be XQS into IDS, or we can write this in terms of the inductances. So, we have omega E LQS into IDS. This also we can write in terms of the inductances. So, we have omega E into LDS, and here we can add the resistance drop. The resistance drop in the q axis is RS into IQS. So, we can have RS IQS, and then we have the resistance drop in the d axis is RS into IDS. So, this is RS into IDS, and then we can complete the phasor diagram by drawing the voltage, and the voltage is applied voltage that we can call VDQS. And what about the current? The current is here IA, and the current will have two components as we have already discussed. This is IQS, the q axis component, and this is IDS, the d axis component, and this angle is the angle that is gamma we have seen previously. So, this is the phasor diagram of a synchronous machine in the steady state condition, and here the power factor angle is theta, and this power factor angle is angle between V and I, we can call that to be theta. So, this shows the various components of the voltage drop in the d axis and the q axis respectively, and we have also seen the torque equation, and from this we can find out the conditions for the maximum torque. We also can find out how we can change the current to control the torque. This will be discussed in the next lecture.